So today we are going to start with the next topic, that is dynamic programming. See, we have been studying the various kinds of data structures for solving the various problems efficiently, and then we moved on to the various algorithms which can help us in solving the various kinds of problems that exist in the real world. So depending upon the complexity of the problem and depending upon the type of problem, we use different kinds of algorithms, right? So we studied about the greedy algorithms which are used for solving the optimization problems, where we have the goal or the objective, maybe to minimize the, you can say, the cost, or to maximize the profits, or something like that, So whenever we have such kind of objectives, we use we say these are the optimization problems, and we use the algorithms which can help us in finding the near optimal solutions. So previously we have studied about the greedy algorithms which are used for solving the optimization problems. See, see, when we study about the various kinds of problems, the question arises: why do we have the various kinds of algorithms? So, because the problems that we have, they have because of the, you can say, the different nature of the problem, we need to have the different kind of algorithm in order to find the solution of that particular problem. When we are using the divide and conquer algorithms, in that case we know we can use the divide and conquer algorithms only when because in the divide and conquer algorithms, what do? We convert the small problem, large problem, into its sub problems till it is small enough that cannot be converted into smaller sub problems, right? So once we have reached to the smallest unit of that particular problem, then we solve that particular problem. So we say we are dividing the complete problem into its sub problems, and these sub problems are independent of each other, which can be solved independently. So we apply the divide and conquer strategy, then we solve each sub problem independently, and then we start integrating the solution of all these small sub problems in order to get the final solution for the complete problem. So here we say it, when we can apply the divide and conquer strategy only when the sub problems that we are trying to convert, they are independent of each other. So we cannot use the divide and conquer strategy whenever we have a problem whose sub problems are dependent upon each other. So in that case, what do? If we have to solve a particular problem where the, you can see, the sub problems are dependent upon each other, so in that case, we say that divide and conquer strategy is not applicable. We have to apply some other algorithm which is suitable for solving such kind of problems. Then you can say we use for solving such kind of problems, we go for the dynamic programming. Then another difference that we see if we compare the, you can say, the greedy algorithms, because greedy algorithms are also used for solving the optimization problems. See, when we are using the greedy algorithms, we start from the, you can see, we are not actually finding out all the solutions. We are just trying to be greedy, and at every stage, as we have seen in the various algorithms that we have worked upon, we are greedy. So we what do? We are finding, we are taking up the minimum first, and then at every stage we are taking the minimum path when we are trying to solve some path problem. So at every stage we are being greedy, and we try to take up the best solution, and then we just reach out to the final solution. So in that case, we say we are moving. See, in that case, in case of greedy algorithms, we are always focusing on finding the single solution. So, right, and the greedy algorithms, they have a drawback that because it what seems to be best in the shorter run may not be the best in the longer run in various in certain problems. So this is the drawback of the greedy algorithm. So on the contrary, if we see that use the dynamic programming for solving the optimization problems, dynamic programming, we basically find out all the solutions, and after computing all the solutions, we choose the solution which is the best. And this dynamic programming, it is basically based on the principle of optimality. That means at every stage, So that means in the complete path at every stage we will be taking a decision whether this is the best or not. So this is you can say the difference between the greedy algorithm and the dynamic programming and the divide and conquer versus dynamic programming. So the various kinds of applications that we try to solve using the dynamic programming, they are the zero one knapsack problem, shortest path using Freud virtual coinage problem, matrix chain multiplication, longest common subsequence, longest increasing sequence, string editing. So these are the various problems that we try to solve using the dynamic programming, and they are good at providing such kind of solving these kind of problems. So as we have already discussed how the dynamic programming is different, or you can say what is the difference between the divide and conquer strategy and the dynamic programming. And we have also, I've just told you what is the difference between the greedy algorithm and the dynamic programming technique. So the greedy method, they have a local choice of the sub-problems where DB would solve all the sub-problems, then select one that would lead to the optimal solution, right? So this is how we use the as I said, your dynamic programming. At every stage we take the decisions, and so it is we say it is based on the principle of optimality. Right. So let us take one example and try to understand what makes the difference when we are saying whether we are using the dynamic programming and the other greedy algorithm approach, or the divide and conquer strategy that we apply. So here we say, let us say this example, why this is fit for solving the dynamic approach, because here the solutions are not independent of each other. Each solutions depend upon the previous solution, right? So where we say, like, if we have to find out the Fibonacci series, then Fn is equal to Fn minus 1 plus Fn minus 2, where with F0 is equal to F1 is equal to 1. So in the Fibonacci series, we use the new number. The next number in the series is the sum of the previous two numbers. So unless we know the previous two numbers, we cannot find out the nth number. So that means there is a dependency on the previous sub-solutions. So if we are given n, how do we compute Fn? So let us say we use the recursive techniques. And if when we are using the recursive techniques, in that case, while solving the Fibonacci algorithm, we know at every stage, we see in the when we are using the recursion, in that case, we are moving following the bottom top down approach. Let's say n is equal to 5. So if we pass this number to this particular function, in that case, it is going to again call the two functions, that is f4 and f3. Then again f4 and f3 will be called again to call for f3 and f2. So until we reach this particular part, if n is equal to 0 or n is equal to 1, return 1. Till we reach to this particular stage, we are not able to get the complete solution. So we always, you can see, if we make a tree, this will start from 5, 4, 3, 2, 1. Like we will have two branches, one on the left hand side subtree and one we will have right hand subtree. And then for this recursion, if we can see the running time for this recursive function, this is equal to Tn is equal to Tn minus 1 plus Tn minus 2 plus over, and Tn is greater than equal to Tn minus 1 plus Tn minus 2 for n greater than equal to 2. So you can say that Tn grows at least as fast as the Fibonacci number themselves. Then if we say that there is a fun fact which says that like 5 power n, where 5 is equal to 1 plus under root of 5 by 2 is the golden ratio. That means it increases exponentially. So let us see how why we are saying this particular uh, so here you can see, if we see when we apply this, if you do the experiment with this particular formula, in that case you will observe that with the increase in the value of n, here you can say horizontally we have the n, n is a number, nth number who's the till we want to find out the Fibonacci series, and t is on the y axis we have the time. So how much time it is going to take to compute the Fibonacci series up to nth numbers. And you can say for a small rise in the number, that is from n is equal to 0 to nth 2022, so the time amount of time taken is very less. But beyond that, the time is increasing exponentially quickly. So the exponential value is also very fast, which is not good for solving the large, computing the large Fibonacci series. So what that means, recursion, finding the Fibonacci series using the recursive algorithms is not a good approach. So in order to get rid of this solution, let us say, see, this is how, when we are solving this Fibonacci series, if we see what is going behind the scene, this is how the recursive calls are being made. So here the same color, the numbers which are same in color, they are representing the same numbers. Here you can see, if we want to find out the Fibonacci number 8, the Fibonacci series for the number 8, then it is going to make a recursive call to 8, because it is fn minus 1 plus fn minus 2. So we are going to have this particular series 8 minus 2 and 8 minus 1. So again 6 minus 2 and 6 minus 1, 7 minus 2 and 7 minus 1. So here you can see the problem is that although we have if we have once computed the Fibonacci series up to the nth number 4, at every stage, see, on the different branches, on the left hand side we have 4, then on the right hand side branch of 6, again we have 4, then we have 4 on the left branch of 7, we have 4 on the right branch of 7. But these you can say, although we may have computed that the nth Fibonacci series for the fourth number, up to the fourth number, but these tasks are being repetitively done. That means a redundant task is being done, which is taking huge amount of time to again compute the same series. So you can say the various subtrees, they are similar along the multiple branches. So we can say, if we are able to find out some solution, if we are able to find out some strategy, that once we have computed the nth number, Fibonacci numbers for the nth number, let us say Fibonacci series for 3, we have already computed, then if in any of the other branches we need to have the Fibonacci series, then we can pick up from there. So that means we are looking for some memorization strategy, or we are looking for something that we can keep a track of, that we have already computed the nth series for this particular Fibonacci series for this particular number, whether it is 4, whether it is 3, whether it is 2. So if we are able to do this particular task, so you can say we are able to reduce the complexity of this particular problem. So this is what is being done when we are going to apply the dynamic programming problem algorithms. So there's a lot of repeated computation. So maybe this would be better that if we use this particular thing, the simplest, if you can recall the simple formula, rather than using the recursive technique, what do? We use the iterative technique. So iterative technique, we know we have two methods to solve compute the Fibonacci series. Either you write a recursive function, or you use a iterative function. So you have to understand that for what kind of problems recursive solutions are better as compared to the iterative solutions. So you can say for the Fibonacci series, your iterative solution is faster as compared to the recursive solution. So here you can say this is how we are computing. So at every stage, what we are doing, see, we are going to compute the values of the nth number, and this is not going to be the top-down approach, it is a bottom-up approach. So here we are not going to start from the largest number, we are going to start from the smallest number. Here we know what is the formula. We say that for I is equal to 0 and I is equal to 1, we are going to directly print the values from the bottom. So 0 and 1 are already printed. Then for we start the loop from 4 I is equal to 2 to n, and maybe 6, 7, 8. Let us say here in this case it is 8. Then fi is equal to fi minus 1 plus fi minus 2. So if it I is equal to 2, then 2 minus 1 is 1 plus 2 minus 0 is 0. So 1 plus 1 is, so we are able to get 2. So here you can see this is how we are going to compute the complete Fibonacci series, and we are not using the multiple computations as compared to what we have done. You can say there are no repeated computations for this particular series as it is there in the recursive function. So you can say for this particular, and this is called as the dynamic programming approach. Now in this dynamic programming approach, what we are going to do here, you can see the recursive formula. If we see the time slots, here you can see when we are comparing the time slots, so from 0 in the you can say for n numbers, ns series, that means you are computing the Fibonacci number for, let us say, for n is equal to 5, ns term is 5, 5 Fibonacci numbers, 10, 15, 20, 25 numbers. So here you can see that faster Fibonacci, the current one, that is the iterative one, it has a better running time as compared to the naive, that was the recursive technique that we have used. So that means for larger values of n, this iterative approach is far better for computing the Fibonacci numbers as compared to that of the recursive technique. So what are the properties? Now let us understand what are the properties of the dynamic programming, as we have already seen a problem which is better at providing the solution when we apply the dynamic programming technique. So it has an optimal substructure. That means optimal solutions to the sub problems can be used to find the optimal solution for the original problems, like Fibonacci fi for I is equal to less than n. So here you can see we are finding the optimal sub solutions, and then we are using it to find the solution to the problem, the complete problem. So it is following the bottom up approach. Then overlapping sub problems, the sub problems show up again and again, as we did. Both fi plus 1 and fi plus 2 directly use fi, and lot of difference of I plus indirectly uses fi. So what do we do when we are applying the DP? So we characterize the structure of an optimal solution. We recursively define the value of an optimal solution, and we compute the value of an optimal solution. Then we compute an optimal solution from the computed or the stored information. So that means we whatever information we have already stored, from that that information will be reused, so that we don't have to perform the computations repeatedly. So the repeated computation part, which is there in the recursive part, that is being eliminated when we are applying the dynamic programming approach. So we have two ways to implement the dynamic programming solution. One is top-down approach and another is bottom-up approach. So in the top-down approach, we can imagine it like a recursive algorithm, but to solve this bigger problem, recurs to solve the smaller problem. So Fibonacci series, we make recursive calls on n, and then see, we are not going to exactly use the recursive technique. Complete recursive technique is not being used in top-down approach. It seems to be like the recursive, but there are certain changes that have been made, that in order to eliminate that repeated computation that we see over here in this particular example. So how this recursive technique is being modified in the dynamic programming is, now we are going to keep our track of all the you can say the numbers which have already been computed. So that means in the dynamic programming, a table is maintained, or there is a concept of memorization. So this memorization is implemented in the form of, you can say, a particular table which keeps a record of the numbers you can say the numbers, or you can say the values which have already been computed. If the you can say the Fibonacci series for 4 is already being computed in any one of these branches, it will not be done again. So here you can say at the bottom of See, if we see because it is following the bottom up approach, so we start from the top, but as we go down and we are reached to the first four. So on the right hand side, so once this four, if it has been the Fibonacci series for this four has been computed, this will be stored somewhere in some table, and whenever at any of the branch we again come across four, it will trace back to this the value, stored value, and the complete computation will be eliminated, and it will directly pick up the value from that particular table. So we are going to follow the recursion, but you can see the solutions are being stored in the tables, and then we are going to use them as it is. So for and the bottom approach, as we have I have already told you, for the Fibonacci, we fill in the F0 and F1 first, then bigger problem is F2, then bigger problems are Fn minus 1, and finally we solve the real problem of Fn. So we move from 0 to 1, and then 2, 3, 4 up to the nth number. So this is the bottom up. So as I've told you, there is an idea of memorization that is being retained in the form of a table that keeps an entry of all the values that have already been computed. So when a sub problem is first encountered, its solution needs to be solved, and then it is stored in the corresponding entry of the table, as I've told you in the corresponding example of the Fibonacci series, because we see the repeated computations of the Fibonacci number 3, 2, 1, 4. So all these things. So whenever we come across any of these numbers first in any of the branches, so in that case, it is solved over there first, and then its value is stored in the corresponding entry of the table. And if the same sub problem is encountered again in the future, we just look at the table and we take up this value. So this idea is called as memorization. So let us solve one problem of one knapsack problem using the dynamic programming approach. So can anybody tell me what